Hello, welcome back. This is the 23rd of August. I'm getting a little bit of a late start today, so I ideally just want to dive right in, to be honest. So where we got up to yesterday was we were looking at the CSES problem set. We got up to permutations. And this one is around basically if a number is what we call beautiful, printing a permutation of that number being a beautiful number. A beautiful number is basically any, for number n, any integer between 1 and n is some kind of permutation of all of those integers, but none of them have like no adjacent element, as you can see here, has a value whose difference is 1. So this specifically here would not be beautiful because there's a difference of 1 between 1 and 2. So like memory wise, or kind of in terms of like, I guess, magnitude of the problem, it only goes up to 10 to the 6, which I guess is like 1 million, 100,000, 1 million, probably a million. So for 5, that is a beautiful number because you can print out this permutation here, which is beautiful because there's none of these elements have a difference of 1. Whereas for a number like 3, there's no solution. So what I kind of figured yesterday is that actually 3 and 2. I may actually just hide my terminal here for a minute, or at the very least make it smaller. So 3 and 2 aren't beautiful numbers, but I realized that when I was explaining stuff yesterday, actually neither is 4. So there's a difference there. Although actually, yeah, and then there's a difference of 1 there. So 4 is not a beautiful number either. But really what I was kind of thinking about today is that if we take this solution that I'm trying to do here, building a vector and basically going by pairs is a little bit unnecessary. I don't think you necessarily need a data structure to actually kind of implement an algorithm that can print the sort of beautiful array. So I'm going to actually make a new solution here and probably put it underneath so that we have like a little bit of a split screen. I'm going to copy probably all of this, and kind of use that in planning the second part, or the second solution rather. What I think we can do is probably actually borrow all of this and obviously round that out. We're gonna need IOStream and CMath for this because we need floor, and we'll use the std namespace. I don't know if I want to call this LHS. I think I can call this like mid or middle. But it is definitely the floor of our number divided by 2. So if n is 3, n is 2, or n is 4, there is no solution. But then if we're taking kind of this floor of here, then we need to know if basically if I just do this in Python, if I was to do kind of the floor of 13, that gives us 6. Whereas if I was to do the floor of 14, that's 7. So we kind of need to have like a check basically that says if you take the floor of a number, although actually I think that's just whether the number is even or odd. Okay. So actually we can do is even by saying that n modulus 2 true false. So if n modulo 2 is 0, then obviously it's an even number, otherwise it's false. So if it's false, we can kind of take these pairs, but we need to actually include this at the end as well. But if it's even, so in the case of like 10, we just do all of the pairs and display them together. So I think that should work. Now, the only thing I need to figure out from this point is how do we get these pairs? Now, I think this is, you still have these kind of split rows. So between the range of 1 and 5, so our mid here is 5. So between the range of 1 and 5, we print whatever number we're currently at in the range, and then whatever number we're currently at plus the mid point. And then if it's even, we can just exhaust that loop and it's fine. But if it's odd, so let me actually write this down. Iterate in range between 1 and mid for each iteration. Print, so let's call this I. Print I. Print I plus mid. If even number, or actually rather, if not even number, print mid at end. Or just say print mid to tack that on the end there. And I think that should actually be fine. And, you know, it means we're not going to need the vector or the pairs or anything like that. I think this should work. So let's do that. So let's construct a loop here. Can't type today. So between I and mid, we want to see out I, and actually I need to initialize I, don't I, to 1. We want to print out I, and then a space, and then I plus mid, and then another space. Once we've exhausted that loop, if it's not even, we also need to add mid. And that should be fine, I hope. Fingers crossed. So let's go ahead and compile this. And let's try with 5. Okay, so that didn't work. So why did that not work? I guess because with 5... it probably has a weird floor number. Yeah, so that would be 2. So if mid is 2 for 5, I still don't see why that doesn't work. We should always at least have 2. I think it could actually be that it's just not doing enough. Okay, that's wrong. But the idea is there. 1, 3, 2. Oh, actually, even that's not right. Is it really not right? 3, 1, 4, 2, 7, 5, 9, 6, 8, 10 for 10. Let me actually try it with 10. 1, 6, 2, 7, 3, 8, 4, 9, 5, 10. Okay, so that works. It just didn't work properly for 5. I guess because mid was actually encountered. Means it might not always work. What about 29? Looks kind of beautiful to me, except, again, I think it's just faulty for odd numbers. Yeah, so you can see 6, 12, 6 at the end. Maybe we just don't even actually need to check if the number is even or odd. Perhaps. But it does actually need to... It needs to output our number at the end, like our main number, which I don't think it was doing before. Ah, okay. So actually, we do want to check if it's even, but if it's not even, we want to actually output our end number at the end. So we actually want to output n. So now if I try something like 14, that looks good. Let's try it again with 5. 1, 3, 2, 4, 5. Okay, 5. That doesn't work. That is very not beautiful. What about 7? Yeah, even 7 doesn't really work. What about 9? 9 doesn't work. I think I actually realized this flaw yesterday. What we can do, and this is hacky, but we can basically just inject our number instead of putting it at the end. Or in fact, probably what's easier is we can say if if mid minus I is 1 and it's not an even number, then we can see out n plus obviously a space there at the end as well. Let's actually see how that goes. Okay, I did not expect that to work. The problem is, though, I think fundamentally how I've gone about building the beautiful number is wrong. Like the mathematics of how I'm building this, well, it doesn't work for anything less than, I guess, 7 or 6. If I try it with 6, okay, that's fine. But actually, if it's 5, that doesn't work. To be honest, I could brute force it and say that if n is 5, then we can literally just see out the example solution. And then it will work. But that doesn't really, that's not really in the spirit of things, is it? And we actually want to say return 0. So 3 is, ooh. In fact, I can probably tidy that up a bit as well. Ooh. Okay, actually it doesn't like me doing that. And put that in braces. Will it let me do that? Yes. Okay, so that's no solution. That's our hacky answer. Then something like 8, 1, 5, 2, 6, 3, 7, 4, 8. Yeah. Oh man, okay. I cannot believe that's how we're gonna do it. I think what the real answer is that you take your number and you say, okay, so basically, I still think every number is beautiful from 5 onwards, but I think the real answer is that you take your number, you go between, you iterate between 1 and your number, and you print. Actually, I don't know, because that's at the end. It could maybe work if you had a like a double-ended queue or something like that. But again, I mean, I don't think you need that complex a data structure. I might just give this a try and see what it says. Because why not? Maybe it works, maybe it doesn't. Probably not, I imagine. Okay, we have a couple of wrong answers. So I think this is mathematically... Oh, 4 is beautiful. 2, 4, 1, 3. Okay. 6, 7, 8, 9, 10. Random numbers, random numbers. Okay, so it is just those two specific test cases which we can solve for. um... Okay. What I might actually do here is just say, we'll actually do a little bit of refactoring here. So, all we really need is n, and that can do basically this. So if I pop that up here, oops, didn't realize that had a line on it. And instead, what we can do is something probably like case. I don't know if this is how you do it. Then see out 4, 2, 5, 3, 1. Actually, I don't even think I need to return 0 here. Otherwise, we want to solve for n. Oh, but obviously we need our case of if it's 4. What was it? Like 2, 4, 1, 3? Yeah. And we'll see how that goes. And then get rid of those. Ooh, left operand of comma operator. What can we do? Multiple values for case in C++. We need to break after each one. Alright, give me 1 second, just gonna pause here. Okay, so it says here that actually some compilers support like a specific thing in case where you can do that. But I guess what we can do is actually just the comparison. And of course we want to break after each one. Will it not let me do a Boolean case? Oh, okay. So if it needs a constant value, we'll just say 2. Two, 3, 5, 4. 2413. 7 1472536. I think this might be it. This is a really terrible way of doing it, but I can't otherwise work out what the actual like mathematics is behind this. So I might still be wrong as well. I guess it takes a while to do it for a million. I might run out of time. Yeah, I might exceed the time limit. Wrong answer. Or, oh, I guess it's because of 1. Yeah. Okay, so actually, if it's case 1, we break. Yeah. Okay, so this should be correct now. Whoops. It does take its time. While we wait for that, I might read the question of the next one. So a number spiral is an infinite grid whose upper left square has number 1. Here are the first 5 layers of the spiral. Your task is to find out the number in any row Y and column X. First input line contains an integer t, the number of tests. After this, there are t lines, each containing integers y and x. For each test, print the number in row y and column x. So you can have anywhere up to like 100,000 tests or 10,000 tests. 100,000. And y and x can be massive numbers. Alrighty. So this is fine. And actually, all things considered, they didn't take too long. I guess the ones at the end were really big numbers. Yes, they were. Okay. So number spiral. Okay, I think this is doable. Well, of course it's doable, but I think I might know how to do this. I guess you start from... Actually, let's just make our boilerplate. So... these are our number of tests, and then... maybe I should actually declare those outside. And actually they are long numbers. So we read those numbers in. So in their case, they said that in 2, 3, 0, 1, 2, 1. Oh, hang on. Okay, so 2 is kind of going down. So this is 1, this is 2, and then 3 along. Okay. It's that number. 22. 1, 2, 3, 4. 1, 2, 3, 4. Mm, 16 plus 6. Okay. What I'm looking for here actually is the pattern. How to do this. I don't think you can get it from your Y and X coordinates. Yeah, I'm looking for the pattern here. I don't quite see it. That's 2 and so 24 would be 2 and 5. Twenty-three is 3 and 5. 21 is 5 and 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 3, 4, 5. 1, 2, 3, 4. So, what I'm... There's not really any kind of hard and fast rules to this. At least not ones that are jumping out at me. Nine, 8, 7, 14, 19. 15, 14, 13. Hmm. Six, 9, 8, 7. What there is, I believe, is that there's some kind of formula for working this out, because you wouldn't build a data structure for your in to represent this infinite grid, especially when these numbers can be so big. You just wouldn't do that. But I'm I'm just going to map this out in terms of what's being added each time. So here it kind of looks like one, two, three, 4, 5, 6, 7, 8. And let's go one more. So this is actually plus 9. The 10 is plus 9. 11 is plus 10. 12 is plus 11. But then 13 is plus 12. 14 is plus 13. Then 15 is plus 14. And then 16 is plus 15. So I think... Let me actually get rid of that. That might make it look a little bit clearer, actually. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. I guess when you have a... When you're given a number... There's kind of a principle in which you want to do this. If you have one, 4, 5, 16, 17. One, 3, 9, 6, at 5 even. I really don't see the pattern in all this. Has to be a way of getting that number. There must be some kind of formula for getting that number. Because I don't think you would want to just produce this grid up until the number that you're actually given there. I mean, I think that I really don't know. I don't know. This probably is quite an easy nut to crack. Yeah. So out of the 30,000 people who submitted to this one, only 3,000, I guess, haven't got it spot on. A lot of submissions here. Whoa. So rather than distract myself by looking at those, I can think about this a little bit more, but I'm not sure if I'm going to get very far today. I probably need to chew on this for a bit because I don't see the pattern. Five and 4 and 4. 5 and 8 makes 13. 16 and 5. 12 and 4. 4 and 4 and 3. No. When you follow it through, and I probably need a pen and paper for this. When you follow it through, there's kind of a kind of a path to it. 1, 2, 9, 4, 3, 8, 5, 6, 7. You're kind of going like 1, 2, 3, 4, 5, 6, 7, 8, 9. And then you'd go down. You kind of go, it's flipped, but this is your 1. You kind of is this a like a representation of Fibonacci or something? It sort of looks like it. It's the series of numbers. It's found by adding up the 2 numbers before it. 5 is 2 plus 3. Okay, so Fibonacci, this is not. I'm not sure if this is relevant. Plus it also grows exponentially. Okay, that might not be relevant. But somehow, surely these 2 things play a part in whether, well, like these 2 inputs play a part in our result. 1, 2. So 2 and 3, 1, 2, or 1, 2, 1, 2, 3 gives 8. No, I really don't see. I don't see the answer for this one. I think when we kind of map out the spiral, you always this will always be a difference of 1. So actually the next number that would be up here is 26, which does kind of help. Maybe that could be a clue. So there's always going to be a difference of 1 there. Now this is 4 along. 3, 4. But I don't know how you... Okay, also here there's a difference of 1. Then 3, then 5, then 7, then 1 again. Also, if it's relevant, these are odd numbers that transition to an even number. And these are even numbers that transition to odd numbers. So it kind of goes like even, odd, even, odd. And 2, 3, 1, 2. What do you get from 2 to 4? Or it's kind of like, how do we get to 14 given a function where our input's like 4, 3? I'm sure this is obvious, but I just don't see it. Really here it's just seems to be more of a mathematics question than anything else. Number of hacks 0. Oh. Okay. Number spiral. Don't see the pattern. I wonder if it's the... Hmm. Is this right? Is it to do with square numbers? Because if we said we wanted to grab 8, well, actually, 8... Well, if we have the input 2, 3, if we take 2, 2 squared is 4, and then 3 squared is 9, that doesn't actually help us, I don't think. But it is interesting though, because 5 squared is 25, but then also 4 squared is not 10. I guess everything alternates as to whether it's a square number or not, maybe? 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36, which is a square number. Also, coincidentally, it's the 6th one down. 1736. Okay, this might actually be a very big clue. So actually 6 squared, yeah, is 36, which is what would be the number down there. But then 2, 3, I mean... 1... 2 squared is 4. And 3 squared is 9, but how does that give us 8? I don't really see how you get from one to the other there. 4 and 2. 4 squared is 16. And... no, minus... Literally minus 1. I'm sure this is something to do with square numbers, but I just don't see how we can use that. Hmm. I may have to have a think about this one and then come back to it tomorrow. And I'll leave it at that. So, yeah, stay tuned. I will chew on this as much as I can and see if I can think of a solution for this one. But otherwise, I'm going to be here all night. So I'll end it there. See you in the next one. Bye bye.